Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject, like share subscribe for daily learning videos.
In this problem, we're asked to figure out the net magnetic field at particular locations that are close to two long current carrying wires. So let's just draw a diagram of what's going on here. So we have what we'll call wire 1, and that's going to be carrying a current, we'll say up, current I here. And we have equidistant between this wire and the next one, this location of point B that we care about. And then we have equidistant from there, wire 2, which is carrying a current, the same value of current I, but in the opposite direction. And we have a location A here we're also interested in. We're given several distances, right? So we're given the numbers in the book, but I'm just going to label this here as a distance from wire 1 to location A. We'll label the same things here. So we have a distance from wire 1 to location B. We have a distance here between the two of them. We'll call that a distance of big D here, just to label that. And I think that's all the distances we need to know in this problem. Okay, so again, we're asked to figure out what the net magnetic fields are at locations A and B. So that really just means we need to figure out, one, what the magnitudes of the magnetic fields are from each wire at those locations. And then we need to figure out what are the relative directions of the magnetic fields from each of the wires at that location. So that's going to tell us what the magnitudes are of those magnetic fields, and then it's going to tell us whether we're going to add or subtract them together. So let's think about the directions of the magnetic fields due to each wire in each region of space that we're going to care about. So let's think about wire 1 first. We'll use red here for wire 1. Rewrite wire 1 here. Okay, so for here, we use our right hand rule. We're going to put our thumb along the direction of I, and then our hands are going to curl around that. And that tells us that anywhere to the right of wire 1, we have magnetic fields going into the page, and anywhere to the left of wire 1, we have magnetic fields going out of the page. Okay, so that we know that the magnetic field due to wire 1 at location A, well, we know that that is going to be going out of the page. Okay, good to know. And at location B, we know that the magnetic field from wire 1 at location B is going to be not going out of the page, but into the page. You write that X and circle there. Okay, that's going into the page. So that's good to know. That's going to help us tell us whether or not we need to add or subtract this particular magnetic field from wire 1 to the magnetic field created by wire 2. So let's think about that as well. We'll use green for that. So we do our right-hand rule for this wire, wire 2. We put our thumb along the direction of the current, and then we curl our fingers around. So what we'll see is that anywhere to the left of wire 2, the magnetic field created by wire 2 is going into the page, and then anywhere to the right, it's going to be going out of the page. So everywhere to the left, our magnetic field due to wire 2 is heading into the page. So that means when I add the magnetic field from wire 2 at location A to the magnetic field of to the magnetic field at location A from wire 1, we see that it's actually going into the page. So when I think about the magnitudes of these fields, I'm going to end up subtracting the two in order to figure out the net field there. Now, if I think about the region what location B is in, when I add the field from wire 2 at location B, that field is also going in, so I'm going to add the two magnitudes of these fields together in that region. So now that we know how to combine the magnitudes of the magnetic fields from each individual wire at each location, let's figure out what the value of those magnetic fields are going to be. Now, in general, I'll write down here, the magnetic field from a long current carrying wire at a distance r away from that wire is going to be mu naught times the current through the wire divided by 2 pi times the distance we are away from that wire. So that's what I'm going to do. I'm going to use this formula here to figure out what the magnetic field is at each location due to each wire. And then depending on the direction, the relative directions of those fields, I will either add the magnitudes or subtract them. So let's make some room here to do some work. And we'll use our diagrams over here to the left. So for part A, we want to figure out what is the net magnetic field at location A. Well, the magnitude of the magnetic field from wire 1 at location A is going to be given by mu naught times the current through wire 1 divided by 2 pi times the distance from wire 1 to location A. Okay, I think we know all those values, so that's great. Now, the magnetic field from wire 2 at location A, of course, has a similar form. We have the same current through each. The only thing that's going to be different is the distance. So how far away is wire 2 from location A? And we'll see that it's actually the distance D, because that's how far away the two wires are from each other, plus the distance wire 1 is away from distance A. So we're going to be plugging that value in for the distance from wire 2 to point A, the point we care about. Now, as I said before, these two magnetic fields are in opposite directions. So what we're going to actually do here is subtract the two and take the magnitude of that result, just because we want the magnitude at that location. So the total magnetic field at location A is going to be given by the subtraction between my two fields. So I'll take my magnetic field from wire 1 at location A and subtract that from the magnetic field from wire 2 at location A. The pi there. Now there's a lot of things I can factor out, and so we'll see that I have mu naught times I divided by 2 pi, all multiplied by 1 over R1A minus 1 over D plus R1A. Okay, let me plug all these things in. Mu naught is 4 pi times 10 to the negative 7 Tesla meters per amp. Divide that by 2 pi, multiply that by the current through these wires, which is 8 amps. And then we have to multiply that all by 1 over the distance from wire 1 to point A, 0.03 meters. And then subtract that from 1 over the total distance D plus R1A. And that's going to end up being 0.15 meters. So put all that in our calculator, and then the answer to part A, so the magnetic field at location A, is going to be given by 4.3 times 10 to the negative 5 Teslas. Okay, so that is for part A. Now, to keep our diagram so we have some reference, I'm just going to erase this work and start over with talking about location B, and then we'll get to finish this problem. Now, for part B, we care about the magnetic field's magnitude at location B. And so we just have to write those individual magnitudes out. And because the fields are in the same direction, we just add the magnitudes together. So the magnitude of the magnetic field at location, from wire 1 at location B is going to be given by mu naught times I divided by 2 pi. Well, how far away is wire 1 from point B? Well, it's R1 sub B. Right? Okay, now we're going to have to add that to the magnetic field created from wire 2 at location B. Same mu naught I, same 2 pi. And now we are still the same distance away. We could technically label this, right, as R2B, but we know R1B and R2B are the same. So let's just write R1B in as well. And because, again, these two magnetic fields are in the same direction, they just add together. So to get the entire magnetic field at location B, we add these two together. So mu naught I over 2 pi R1B plus mu naught I over 2 pi R1B. Well, that's just two of these terms. And then that 2 on the bottom is going to cancel. So all I really have to write out here is mu naught I over pi r1b. Plug all these things in, and then the magnetic field at location B, move this over here, is going to be equal to 4 pi times 10 to the negative 7 Tesla meters per amp, multiplied by the current going through the wires, 8 amps. Divide that by pi times how far away is point B from either of the wires, 0.06 meters. And what do we know? We plug all this stuff in, we get a magnetic field of 5.3 times 10 to the negative 5 Teslas. And that is the answer to part B and brings us to the end of the problem.